Congratulations on completing the exercise and on generating your first geometric random variable. You should now be able to write programs to generate uniform, Bernoulli, binomial, and geometric random variables. Furthermore, these exercises have hopefully reinforced the links between these various types of random variables. For instance, you now hopefully remember from the previous exercises that the binomial random variable can be generated using this code, and that the binomial random variable is just a sum of independent Bernoulli random variables. This process of taking functions and sums of simpler random variables is in fact the way that we can begin to build up to writing programs to generate the more complex random variables. As a case in point, suppose that we deleted the if statement from the code shown here that generates the binomial random variable, and suppose instead that we just summed up our individual random variables, as shown here. Suppose furthermore that once we had repeated this procedure a number of times, we divided the sum of our random variables by the total number of random variables we had generated. The quantity mm that we would calculate by doing all this would still be random, as it is a sum of random variables, but it would have a distribution that was rather more complicated than the uniform distribution that we had sampled from in generating it. The quantity that we generate using the code shown here is in fact the sample mean for the uniform random variable. As you will no doubt remember, the sample mean is computed by taking a sum of n independent and identical random variables and by dividing it by n. The sample mean that we have calculated with this code is thus the mean for a sample of 10 uniform random variables. As you will have learnt from elsewhere, the sample mean is a useful quantity to calculate because of results like the law of large numbers and the central limit theorem. These theorems ensure that when the sample mean for a set of independent and identical random variables is computed from a sufficiently large sample, it takes a value that is close to a special number known as the expectation of the random variable. You may even have seen graphs, like the one shown on the right of this slide, that show how the value of the sample mean changes as the number of samples that it is computed from changes. This graph shows how the sample mean for a set of samples of uniform random variables behaves as the number of samples it is computed from increases. As you can see, because this is a uniform random variable between 0 and 1, the blue curve, showing the value of the sample mean, converges to the expectation for this distribution, which is equal to 0.5 and which is shown in red here. In this next exercise, you are going to learn how to generate a graph like the one shown at the top right of this slide. When the Python code that you create using these blocks is generated, it will ultimately look something like this. Let's take apart this code by starting at the end. What we are ultimately doing is drawing a graph. The x-coordinates of the points on this graph will take the values in the list called x, while the y-coordinates will take the values in the list called mu. Let's now look at what's in these two lists. The list x is populated here. Essentially, x will just contain the numbers 1 through 100, which we can tell by looking at how the variable n is set in the line above, the one indicated with the arrow. If we now look at how the list mu is populated, we see that its various elements are all set equal to the variable sum n divided by n. Sum n is equal to the sum of all the random variables we have generated, so the values in the list in mu are thus the sample means that are generated by summing different numbers of random variables. Hopefully this is now clear and you can do the exercise. Good luck.